Have you ever experienced an application freezing, becoming unresponsive, or simply lagging during a long computation? This common issue creates a frustrating user experience, making software feel slow and unreliable. Imagine a chef who can only work on one dish at a time, meticulously completing each step before starting the next. If a soup needs to simmer for an hour, the chef stands idle, waiting. Now, picture a more efficient chef who starts the long cooking soup, then immediately moves on to chopping vegetables, preparing other ingredients, or even starting another dish while the soup simmers. This is the essence of asynchronous programming. In synchronous programming, tasks execute sequentially, blocking the main thread until each one is fully completed. This is like our first chef, where the application waits for one operation to finish before starting the next. Asynchronous programming, however, allows multiple tasks to run concurrently without blocking the main thread, significantly improving responsiveness. This mirrors our second, more efficient chef. In C#, the async and await keywords simplify this complex concept, making asynchronous programming much more accessible. They are your tools for building responsive applications. The async keyword designates a method as asynchronous, enabling the use of await within it. The await keyword then pauses the method's execution until the awaited task is complete, returning control to the caller. Let's begin by demonstrating async/await in a simple .NET console application within Visual Studio. This will provide a clear foundation for understanding its core mechanics. We'll simulate a long-running task using task.delay, which pauses execution for a specified duration without consuming CPU cycles, perfect for our demonstration. First, observe a synchronous version. Here, console.writeLine, task, delay, wait, console.writeLine. The wait method explicitly blocks the main thread for 5 seconds. When executed, the application will pause entirely for 5 seconds before printing end, demonstrating how the main thread is blocked and unresponsive during this period. Now, let's convert this to an asynchronous version. We'll change the main method signature to static async task main and replace task delay wait with await task delay. The async keyword tells the compiler that this method can be suspended and resumed. The await keyword is the specific point where execution pauses, returning control to the caller until the awaited task completes. With this asynchronous approach, the program doesn't freeze. While task delay is running, the main thread is free to perform other operations, maintaining responsiveness. A crucial tip: generally avoid async void methods, except for event handlers. Exceptions in async void methods are difficult to catch and can crash your application, making async task or async task TA preferable. Now, let's transition to the Unity engine. Unity operates on a single main thread, meaning blocking it will freeze the entire game, a critical problem for game development. We'll create a simple C# script attached to a game object and a UI button that, when clicked, triggers a long process. Observe this synchronous example. Clicking the button executes a system, threading, thread, sleep, call. The game will completely freeze for 5 seconds, becoming unresponsive. This code snippet shows the synchronous on-button click method, where thread, sleep directly blocks the main thread, causing the game to halt. Next, we refactor the method to be async task. We'll use await task, delay, to simulate a non-blocking wait, or await task, run, for CPU-bound work. Now, when the button is clicked, the game remains responsive. The await task, delay allows Unity's main thread to continue processing frames and user input, preventing any freezing. This asynchronous on-button click method demonstrates how await task, delay allows the game to remain responsive, crucial for a smooth player experience. A helpful tip: await automatically handles synchronization context, ensuring that after an await, execution returns to the main thread. This is vital for safely updating Unity objects like UI text or game objects. To summarize, async/await is a powerful pattern for building responsive applications. Let's review some best practices. First, use async all the way up the call stack. This ensures that no blocking calls are made higher up, maintaining responsiveness throughout your application. Second, prefer task T over void for async methods, except for event handlers. to ensure better error handling and more predictable behavior. Third, use task.run for CPU-bound work. This offloads intensive computations from the UI or main thread, preventing your application from freezing. Finally, async/await is essential for creating responsive applications and games, providing a smooth and enjoyable user experience. By mastering these concepts, you're now ready to start building non-blocking, responsive applications that delight your users.